So a lot of today, yes, everything we've gotten through so far is mostly blood, which is a big part of the cardiovascular system because it's the heart that's pumping the blood everywhere. But it was a lot of what's in blood, what does everything that's in blood do? Today we actually get to everything about the heart, which pumps all of that blood. Now, the heart pumps the blood in two different circuits. And it just depends on where it's pumping the blood. Now, it will pump blood to the pulmonary circuit. Anything pulmonary has something to do with the lungs. Now, and I'm like, we'll get through kind of the flow of the heart today, but the right side of the heart, so your right atrium or right ventricle, is receiving unoxygenated or low oxygenated blood. And where you go get oxygen is the lungs. So the right side is going to take that low oxygenated or unoxygenated blood and it is going to pump it to the lungs to go get oxygen. That oxygenated blood then has to go back to the heart on the left side. And that left side is then going to pump the body to all the tissues in the body, to the various systems of the body, so we call it the systemic circuit. So the pulmonary circuit is getting that unoxygenated blood to oxygenate it. The systemic circuit, aka all the rest of your body, is receiving that oxygenated blood, because our cells need oxygen, and then it's going to send that unoxygenated back. So we have a pulmonary circuit to go get oxygen and a systemic circuit, which is dropping off the oxygen. Now, nice little picture, flow of blood through the heart, lots and lots of arrows. Again, we have arrows, and I'm like going into the right side of the heart, and then it's going to pump it to the lungs to go get oxygen. So now it's red. And it's the oxygenated blood goes into the left side, and then it pumps that oxygenated blood out to the rest of the body through all the various systems. And it starts up all back over again. Now, the heart itself is approximately the size of a fist. So if you squeeze your fist together, that's approximately the size of a fist. We dissected hearts already in lab, and I'm like, and yeah, sheep's hearts are pretty close to the same size as our hearts. And I'm like, kind of, different. They vary a little bit, just like your hand varies a little bit in size, so do our hearts. Now, it sits in the mediastinum. It's the middle part of our heart between the second rib and the fifth rib in this intercostal space. It just means in the space in between all our ribs. And 2/3 of it lies to the left of the midsternal line. So we have that sternum, the bone that is right smack down the middle of our body. The heart lies over to the left side a little bit. So when you say the Pledge of Allegiance, where do you put your hand? You put it over on the left-hand side. You take your right hand and it goes onto the left side. It's almost like weird if you try to do it the other way. The reason we do that is the heart is over on the left-hand side. It's a little bit off-centered. So this is just showing them it's hanging out more on the left side of the body than the right. But actually, we're pulling back some of that lung tissue even to be able to see all of the heart. Now, the heart itself, and I'm like, has several coverings on it. One, it sits inside of a double-walled sac, and I'm like, our pericardial sac. However, it also has a superficial fibrous pericardium, which is a lot to say. But here's our superficial, it's on the farthest outside, fibrous pericardium. And you can see all the little fibers there. That helps protect the heart and the cavity, and it helps anchor it to other surrounding structures, whether it's anchoring itself to part of the lungs, whether it's anchoring itself to part of the sternum. It helps anchor it and keeps it in place. It also helps it prevent from overfilling, from stretching too far by having this kind of extra protective, kind of tough, fibrous tissue on the very far outside. Now, if we work our way in, and I'm like, we've got that little cavity and a little layer on either side of the cavity. So underneath that outside superficial fibrous pericardium, we have a deep two-layered serous pericardium. And we have, this may sound familiar from lab, we have the parietal layer and we have the visceral layer. And like the parietal layer lines the internal surface of the fibrous pericardium. It's on the outside. And so I'm like, it's going to line the cavity, but that fibrous pericardium lines, makes up part of that outer cavity, but it lines that inside. The visceral, also called the epicardium, actually is attached to the heart wall itself. And the space in between is called the pericardial cavity, and it's filled with pericardial fluid. Peri just means around. Anything cardi means heart, so this is all things around the heart. And by having that extra fluid, it reduces friction. You have to remember, I'm like, this heart is moving, it is contracting, and I'm like, and we have two different membranes, that every time the heart expands, those two different membranes can rub. Now, that causes friction. What's a side effect of friction, like when you rub your hands together? The heat. This is why we do it in the winter, is we rub our hands together. And I'm like, we don't want our heart overheating. This is a non-stop beating. This is a possibility, if there was no fluid there, that those two membranes would constantly be rubbing against each other, creating too much heat around the heart, damaging tissue. And so we have that nice fluid, reduces friction. We shouldn't have any rubbing of membranes. Otherwise, you end up with lots of other problems. Damage and heat and all that stuff. But just reduces all that friction. There we go. Now, yes, and I'm like, it can occasionally happen that some of that pericardium, one of the layers, becomes inflamed. It's called pericarditis. And yes, occasionally the membrane surface, I'm like, they roughen, and I'm like, sometimes they rub against each other. Sometimes you can actually hear the rubbing. We almost have these little bit tougher membranes because they're inflamed, so they're usually thicker and tougher. And as they start to rub, it's called the pericardial friction rub. And you can hear a creaking sound. It's never good if your heart sounds like it's creaking, like it's an old heart. And I'm like, that's never good. And I'm like, we can also get kind of this inflammation. And I'm like, sometimes it's from the, some creaking. Other times if we have inflammation anywhere around that pericardial cavity. And I'm like, we get excessive fluid in the cavity. So it's not always just rubbing against. We can also have pericarditis from excessive fluid in the heart, or not the heart, but the pericardial cavity. Now, if this has too much fluid on the outside, it's going to push in and on the heart. The heart needs to, when it fills, it has to expand. However, there's too much fluid on the outside, it's not allowing that heart to expand. And so, like, it starts to compress the heart. The heart can't pump as much blood as it needs to, because it can't expand and fill and then contract, because it's stuck. And I'm like, it's called cardiac, the official word for it is cardiac tamponade. Now, what interesting, funny words in there? No one wants to say it out loud. And you're like, hee, hee, hee. And I'm like, the word, yes, I'm like, it does actually have the word tampon in it. The official, I'm like, what the word tampon means is plug. This is actually called a heart plug. And I'm like, it stops the heart from pumping completely. Now, layers of the heart, we already kind of talked about that outer layer, that visceral pericardium that lines the heart, also called epicardium, epi meaning on the surface. Then we also have the myocardium and the endocardium. Again, in lab, we already looked at these because we had identified the different layers. What can you tell me about the myocardium? Based on its name. You know what myo means? It's the muscle layer of the heart. And where do we find the endocardium? It's on the inside lining of the heart. So there was an outside lining, then there's a muscle, then there is the inside lining. So we're going to talk about the myocardium. We already talked about the epicardium. We're going to look at the myocardium. This is the actual heart muscle, that cardiac muscle tissue, that cardiac muscle. Now, the cool thing about the cardiac muscle tissue, most muscle we've been looking at, because a lot of it's been skeletal, they just run like up and down or side to side, but in like the exact same direction. And I'm like, the cardiac tissue, the cells, will start to wrap around. They form these spirals. They form a spiral around each atria. They form this cool, figure 8 around the ventricles. And I'm like, they crisscross, they interlace, they all connect, and I'm like, it just all forms like one big, huge spiral, and then you have connective tissue holding it all in place. So it forms around these ventricles, it forms around these atria. Now, the connective tissue that anchors it all in place, it just anchors all the cardiac muscle fibers together. So these are all anchored together. These are all anchored together. These and so on. We have connective tissue that supports great vessels and valves. We have huge arteries and veins that are going in and coming out of our heart. They have to somehow connect into all of that muscle tissue. They need extra support to anchor them in, and so we have connective tissue that does that. And the connective tissue limits the spread of action potentials to specific paths. We know where action potentials, we'll talk about it today. We know where action potentials we want to start. In lab, you had to kind of like label these different parts. You know, starting here, going down that bundle of his and bundle of branches. By having connective tissue around certain areas, it limits action potential movement. Instead of having, you know, an action potential is not going to go to here to here. It follows a very specific path. The endocardium, as its name says, is the inside lining. It's shown as a white. On the actual muscle tissue itself, it is kind of a whitish, silvery, kind of shiny layer on the inside of the muscle. It's continuous with the blood vessels. So as the blood vessels go in, and I'm like, that endocardium continues out into the blood vessels. So it lines all of the heart chambers, and it covers the valves that are in there. It covers those AV valves. It covers the semilunar valves. So you have that endocardium covering everything on the inside of the heart, including the blood vessels. Now, the different chambers, I'm not going to spend a ton of time on some of these chambers because we already talked about them a little bit in lecture or in lab. But we have atria, as it says way up at the very, very top. Atria are the receiving chambers. So if blood is going into the heart, it's going into an atrium. They receive it. Now, on the outside of those atria, they have those auricles, those kind of flabby-looking tissue, you know, that flabby-looking tissue that you can see on the outside of the heart. Those auricles allow those atria volume to get larger. Those atria can expand when it fills with blood because it has that extra flabby tissue. So it can get larger. The atria, I was going to say, they're small and thin-walled. Partly they don't need a really thick wall. They contribute very little to the movement or the propulsion of the blood. Because where do they send blood? If you're in blood in the atria, where do you go next? Before that. The ventricles. Is that very far away? No, not at all. And so the atria do not need a lot of muscle because they don't have to pump the blood very far. Atria, ventricle, that's it. And I'm like, so they contribute little to the propulsion of the blood around the body because they're just moving blood from little atria down to the little ventricles, and that's it. Now in lab, there are 3 veins that dump into the right atrium. We looked at the superior vena cava, we looked at the inferior vena cava. There is one other vein that dumps into the right atrium. It's called the coronary sinus. And you're like, well, if the superior vena cava is bringing blood from the upper part of the body, and the inferior vena cava is bringing blood from the lower part of the body, where the heck is this coronary sinus bringing blood from? It's bringing blood from the heart muscle itself. If you remember, we have the cardiac, or I was going to say the coronary arteries and the cardiac veins. Those cardiac veins, I know, dump into the coronary sinus. So the fact that your heart is generating low oxygenated, because it's using all the oxygen, low oxygenated blood, it has to get into the circulation as well. So it also dumps into that right atrium. There are 4 pulmonary veins that dump into the left atrium. So 3 veins go into the right atrium, 4 pulmonary veins dump into the left atrium. There's a wall that divides the 2 atrium, interatrial septum. Now, when you were a fetus, we looked at it in the lab, and I put the little poker right through it. And I'm like, when you were a fetus, you had that oval hole, the foramen ovale. Now, after you're born, that hole goes away. And I'm like, but there is a remnant of it. So you can still look inside of a heart and be like, oh, look, there's some tissue where I can see that there used to be an opening. That tissue where it looks like there used to be an opening is called the fossa ovalis. I always think like it's like a fossil of the foramen oval. So you can still see it in there. Now, on the bottom, the atria were the receiving chambers, which means the ventricles in the bottom part are the discharging chambers. So atria receive the blood, ventricles pump it out. So they have a lot thicker walls because they have to pump blood throughout different parts of the body. Now you have a right ventricle and you have a left ventricle. The right ventricle pumps blood into the pulmonary trunk. Goes to the pulmonary arteries, goes and gets oxygen. The left ventricle pumps blood into the aorta, and I'm like, which is the largest artery in the body. Now, do you remember from lab, which ventricle has a thicker wall? The left does. And I'm like, the left ventricle has a thicker wall. It pumps blood into the aorta. And where is blood in the aorta going to? Where in your body is blood in the aorta going to? Your entire body. It's a lot of space you have to pump blood to. So if your little left ventricle hanging out over here in the heart, when you pump, that blood that you are pumping out has to go everywhere, to your fingertips, to your toes, to the top of your head. That's a lot of area. And so it has a nice thick wall in that left ventricle because it has to pump really hard to pump blood through the entire body. If you have blood in the right ventricle, yes, it pumps it into the pulmonary trunk, and where does it go? From the pulmonary trunk to the lungs. Anything pulmonary has to do with lungs. So if you're a right ventricle, and I'm like, and it pumps, it has to pump blood to the lungs. Are the lungs very far away? Nope. And I'm like, they're right next door. So I'm like, it has to pump, but it doesn't have to pump as hard because the blood doesn't have to go very far. And I'm like, it only has to go to the lungs and then come right back. So left ventricle, way thicker wall because it has to pump blood everywhere. Now, on the inside of the ventricles, there are some of these irregular ridges. Let me go back, I've got a picture. There's irregular ridges, and I'm like, on inside of there. And I'm like, these irregular ridges, here we go, there's better pictures. And I'm like, it's called the trabeculae carni. Now, do you remember where in the lab where you've seen the word trabeculae before? In your spongy bone. It made all the rods up in your spongy bone. The inside of ventricle walls actually almost look like the inside of spongy bone. They kind of have all these ridges everywhere. Now, also, we can see inside the ventricles, we have papillary muscles that anchor the chordae tendineae. Just like two big, huge things all in itself. One, and I'm like, these are muscles that anchor your valves. And I'm like, because those valves are attached to things. So we've got our AV valves, and yes, they have to attach to the walls of the ventricle. And so you have your papillary muscles coming up and are anchoring themselves to those little strings coming off of the valves. I'm like, so you can see these papillary muscles come up and anchor themselves to the strings of the ventricles. I was going to say, and between the two ventricles, interventricular septum. I don't remember why I had that on there. Now, so atria, ventricles. Atria receive blood, ventricles pump blood, and then we have valves everywhere between it. Now, star, highlight, you have to know that first very line. The reason why we have valves. Valves ensure a one-directional flow of blood through the heart, which eventually means it's a one-directional flow of blood through the body. Our blood is very specific where it needs to go. Go get oxygen, come back, go pump oxygenated blood. Drop off unoxygenated blood, go get oxygenated blood. These valves make it so that blood is always flowing in one direction, does not go backwards. We do not want blood to go backwards. That's a whole other issues. Some we talk about. Now, they will open and close in response to pressure. If you push on something hard enough, it's like a door, it will open. And I'm like, same thing with the valves. If there's enough pressure pushing on it, they will open. However, that also helps it close. If there's enough pressure pushing in the other direction, it will close. It's like if this door, if it's kind of propped open a little bit, I'm like, if I press that on hard enough, it will open. If I go on the other side of the door and I put pressure on it, it will close. It's the exact same thing with the valves. They just open and close based on the pressure of which direction it's pushing it in. Now, we've already seen these in lab. You have two AV valves, left side and right side. And yes, they have alternate names, tricuspid for the right side. And I'm like, the left side is called the mitral valve or the bicuspid. Don't care which one you want to call it, as long as you recognize the different names, because I don't remember which one I called it on a lecture exam. But they prevent backflow into the atria. I kind of just want like a big picture of a heart up here I can label. All right, you guys have to like humor me with my it's a heart. And I'll erase a few things. Just picture, imagine. Just because I want to get more colors on here. If you remember from the picture, there it looks like little butt cheeks in there. There's the butt cheek valve. There you go. butt cheek. Now, here are my AV valves. We'll kind of connect them a little bit better. And I'm like, that goes from atria to ventricle. You have your AV valves, atria, ventricle. Now, and I'm like, first, what side of the heart is this? This is the right side. So here's my right AV valve or tricuspid. When it closes, it prevents backflow into the atria. It's a one-directional. Blood should always be going from atria to ventricle. If the ventricle tries to push it backwards, it will close the door. And I'm like, it's like going on the other side. I'm like, if pressure starts to go backwards, it closes the door so that blood never goes backwards. So your two AV valves are preventing blood from going back into the atria. Should always be going down and never back. Now, the chordae tendineae, I'm like, I already kind of mentioned it because we talked about the papillary muscles. And I'm like, the chordae tendineae, there are like, it's not like my most beautiful picture, but I'm like, there are little strings that, yes, anchor, and I'm like, onto little papillary muscles. There we go. Strings into the actual ventricle wall itself. It helps hold those flaps in a closed position until they need to get open. I was going to say, here's the chordae tendineae. Here's a way better picture than my drawing. Little chordae tendineae. Sometimes they're even nicknamed little heart strings because they look like tiny little strings hanging off those ventricles. And they're attached to the papillary muscles in the ventricle. And yes, it'll, hold those valves closed unless something is pushing them open. This is just showing. And I'm like, when the atria contract, and they both do it at the same time, they will push their blood into the ventricles. It will, the pressure in those atria, not that they have to pump blood very far, but they can generate enough pressure to push the blood into the ventricles. So they can generate enough pressure to open those valves, and then it opens them up, and all the blood goes into the ventricles. Now, when the ventricle walls start to contract, they generate enough pressure to close the doors. They close the valves so that blood doesn't go back up into the atria. So the atria contract first, exact same time. They open those valves, put blood in the ventricles. When the ventricles start to contract, they close the door, they close those atrioventricular valves, so it can't go backwards. But there's two other set of valves too. There's the semilunar valves. There's the aortic semilunar valve, and there's the pulmonary semilunar valve. Which is, I'm not as good as drawing all these blood vessels on here. They're a valve. They prevent backflow. They help make it that unidirectional flow. Now, if you are in this chamber, what is this? Right ventricle. And we're going to pump it through this. What valve is this? This is the pulmonary. We'll divide and go to the two lungs. And I'm like, here's your pulmonary valve. When the right ventricle contracts, and I'm like, it's generating pressure, one, to close the door here, so it doesn't go backwards, but it's also generating pressure to open this door. So it closes one door and opens another door. And so it is going to pump blood from the right ventricle into the pulmonary trunk and into the pulmonary arteries. Now, when blood gets up in here, it doesn't like to be, big open area, smaller area. It generates pressure by being in the small area. It will close the door behind it. On the other reverse side, your left ventricle, thick wall, and I'm like, it's going to pump blood into the aorta. And so a little butt cheek underneath there. And I'm like, when it generates pressure, it opens that door and then sends blood up into the aorta. And again, once it's in the aorta, it doesn't like to be under pressure because it's in a smaller area. It closes the door behind it. There we go. I was going to say, this is showing just some of the valves, and I'm like, just showing different valves up there. But I'm like, we saw these in lab already, and I'm like, some of these different, here's your tricuspid, your bicuspid valve. And I'm like, I don't think I had another one. But there are some things that can happen with valves. One, you can have what are known as incompetent valves. A lot of times they don't close all the way. And I'm like, so if you don't close the door all the way, stuff can sneak back. And I'm like, and so this is called an incompetent valve. The blood is going to start to backflow. And instead of having all of it go here, now you can have a little bit sneaking back. Usually it doesn't all. And I'm like, because you would have serious complications if it all flowed back. And you probably would have had heart surgery right away. And I'm like, but some of it can sneak back. And your heart's like, oh, this blood's back here. You pump it back again. And then some of it sneaks back. And your heart has to keep repumping the same amount of blood. Again, if you're on the right side, this is unoxygenated blood that's never picking up oxygen. Or if you're on this side, now you have oxygenated blood that's never getting pumped out to the body to drop off oxygen where it needs to. So it kind of depends on which valves. Like if you're not getting enough oxygen, and I'm like in your blood, or you're not dropping it off, depending on how severe it is, you're not getting oxygenated blood to your tissues. Sometimes the first signs are you're just tired all the time. And I'm like, you're just not getting oxygen. You're winded. You walk up one flight of stairs, and I'm like, and you're completely winded. And some of you are like, I do that anyways. This is like, if you do any small amount of exercise, like you get up and walk across the room and you're like, oh my God, I'm winded. That might be an indication, and it'd be the only thing, and I'm like, that could be happening, but it might be an indication that, you're not circulating and oxygenating your blood like it should. You can also have that those valves, those flap, start to stiffen. And I'm like, which if you've got stiff valves, it's harder to open them. It's like if you have a sticky door, it's harder to push it open. And so it constricts the opening because you might not be able to open it all the way. And your heart muscle has to exert a lot of force just to be able to pump the blood in that one single direction. Again, you can be tired. Your heart may start to enlarge because it's trying to overwork, trying to push that blood through those sticky valves. Now, what they can do is they can now replace those valves. One, you may get a mechanical valve, aka it's metal. You have a metal valve in there. One, they may get valves from animals. Pigs and cows have valves very similar to ours. Or you may get a cadaver valve. And I'm like, they can actually take the valves, and I'm like, out of the cadavers, they freeze them. And I'm like, in case someone needs one, and they'll put in a cadaver valve into you. Now, again, and I said, I'm like, these are things where I'm like, who thinks of these things? I have no idea. The mechanical valve, they literally go in there. We're looking from atria down into ventricle underneath here. They cut out where that AV valve was. And I'm like, it's gone. And they sew it in. They stitch it up in there. They sew in this metal valve. To me, I always think they kind of look like those garbage cans, the circular garbage cans, and if you push it in, you put it in and then it closes shut. They kind of look like that. And yes, and I'm like, when the pressure's high enough, it pushes the valves open, but otherwise they normally click back into, a closed position. Now, interesting part about that, because I'm always nosy when people have medical procedures done, and I'm like, tell me more. And so one of my husband's friends, I was chatting with his wife, he had this done, and she said the coolest part, or at least their kids think it's the coolest thing, you can hear when these things close, they clink. And so when their kids listen to dad's heartbeat, if they put their ears on their chest, they can actually hear the heart clinking. So, they think their dad's like a part robot. And I'm like, because they've got metal in there, you can hear clinking. It would be kind of cool, but that just looks like a scary procedure to have to go in. But it happens all the time. They do it quite often. Now, this is the pathway of the flow of blood through the heart. It looks like a lot, but this goes through each chamber, which valves it has to go through, where it goes to get oxygen, and I'm like, which artery, which vein. You have to know the flow of blood through the heart. And some of you are like, look at this, and you're like, holy cow, that looks horrible. If you like pictures better, here's another picture of it. And I'm like, this is showing blood goes into the right atrium. Before it gets to the right ventricle, it has to go through the tricuspid valve. From that right ventricle, it wants to get into the pulmonary trunk or the pulmonary arteries. It has to go through the pulmonary semilunar. It goes to the lungs and picks up oxygen. From the lungs, it has to bring that oxygenated blood back to the heart, so it has to travel through pulmonary veins, those rare veins that carry oxygen, and now we're back in the left atrium. So now we're on the left side of the heart with lots of oxygenated blood. So the systemic circuit starts there. Left atrium, lots of oxygen. But to go from atrium to ventricle, you have to go through that mitral valve or bicuspid valve or left AV valve, whatever you want to call it. From that left ventricle, we have to pump blood to the body. But before it can leave the heart, it has to go through the aortic semilunar valve or aortic valve into the aorta and then sent out to the entire body to drop off oxygenated blood. And then once it's dropped all the oxygenated blood off, it starts back up there at the right atrium. And I'm like, so it's a flow of blood through the heart. And I'm like, this again is kind of showing, I'm like, it's, going step by step, following the actual blood, pumping blood out. Now it goes to the lungs. Now it has oxygen, following it back in. And it goes all the way around. You have to know flow of blood through the heart. I guarantee. And I'm like, there's going to be a question, or two, I don't remember. And I'm like, on your next lecture exam, which is Tuesday, and I'm like, that says, if blood is in this chamber, and I'm like, where does it go next? Or, what valve would it have to go through? And I'm like, after it leaves this particular area. And I'm like, or I might ask something, if this valve is incompetent or it's not working, flow of blood from this area or this chamber would go where? Going backwards. So it might not be going point A to point B. It's also what happens if the valve's working, what's point A to point B to point A. So you have to know a flow of blood through the heart. I think if I remember correctly, there's like 2 or 3 questions on there. And I'm like, that have to do a flow of blood through the heart and valves, what valves you have to go through, and if they're not working, where do you go if you go backwards? Now, pathway of blood through the heart, equal volumes of blood are pumped to the pulmonary and the systemic circuit. And most people are like, there's no way, because the pulmonary circuits, it's only the lungs. That's it, compared to the entire body. Why would there be the exact same amount of blood in the lungs, that we're picking up oxygen than the body? Well, it's a unidirectional thing, and I'm like, we're still sending the same volume of blood to the lungs. That lungs split, that blood in the lungs splits a whole bunch of times. Lots of capillaries, lots of areas to pick up oxygen. And I'm like, and then yes, send the same volume of blood, goes out through the entire body to drop all that oxygenated off. The only difference, same volume, 2 different systems, different pressure. The pulmonary system, we don't need as much pressure to pump that blood to the lungs and back. It's not very far, doesn't have to go very far, so lower pressure. However, the systemic circuit, it's a long way that blood has to travel to the tips of your toes and your fingertips. So it's a higher pressure. It has to pump it all to those different areas. And yes, we saw this in lab. That left ventricle wall is going to be about 3 times thicker than the right ventricle wall because it has to pump that high pressure blood through the entire body. And so it needs extra strength, so it has a thicker muscle. Now, with all of this pumping, the heart needs oxygen as well. It's made up of tissue. It needs oxygen. And so it has its own supply of arteries and veins that not go to the entire body, but we also have to pump blood to the heart itself. So this is our coronary circulation. So there's pulmonary and systemic, but then there's the lesser discussed fact that there's blood that's going to the heart and then going back, on the veins going back into the heart. The blood that's inside of the heart, people are like, well, can't it just get oxygen from the blood that's inside? It can't. And I'm like, those chambers inside the heart, they're just pumping blood to the lungs and to the actual body itself. There's no oxygen transfer. There's no oxygen dropping off from any of the blood that's inside the heart. So that heart muscle has its own supply of arteries and veins. Now, and I'm like, we kind of already know this. And I'm like, your arterial supply varies among individuals. So everyone's arteries on the outside of their heart varies a little bit. But there's lots of junctions between the different arteries all around their heart. See if I've got a picture. And I'm talking like junctions. This one's showing a few of them. And I'm like, but there's different junctions. This actually isn't really showing the few of them. And I'm like, as they start to branch, some of these like to join up with each other. They're just not showing all of it because they're showing the major arteries. And I'm like, but they like to be able to branch and split amongst themselves. Reason why they like to branch, if we've got these 2 arteries and they connect to each other, if there's a blockage in one of them, it can try to reroute the blood into the other one so that you still get oxygenated blood. So you've got all these little junctions trying to connect the arteries and the veins around that heart itself. However, if you have a full blockage in some of these coronary arteries, like the main ones that haven't started to branch yet, and I'm like, it's too bad. Does anyone know what that's called if you have a full blockage in a coronary artery? It will cause a heart attack. And there's an official word for it. I don't remember where I get to it. Myocardial infarction. It's a heart attack. We'll get to it in a second. And I'm like, this is just showing some of your major arteries. no way, you don't have to know them all. And I'm like, the main ones, they do come off the aorta. And I'm like, yeah, there's big arteries that come off the aorta you have to know in lab. And I'm like, you don't have to know these. But there are other arteries that are coming off the aorta. They're kind of tucked behind there that are bringing oxygenated blood to the heart. And I'm like, same thing, we've got veins. And I'm like, we've got all of those cardiac veins all around the heart. They eventually all join together and dump into that right atrium, superior vena, inferior vena cava. And we've got these coronary, it's got the coronary sinus, just where all the cardiac veins are dumping into and into the right atrium. But if you have a big blockage early on in one of those major arteries, big blockage, that means any tissue that needs oxygenated blood that's below that blockage is no longer going to get oxygen. What will happen to tissue that doesn't get oxygen? It dies. I don't remember if I have it on there. And I'm like, you'll have, cell death. And I'm like, and so the higher up on the artery, the more damage it will cause, because the more tissue death it will cause. Now, when your cells are dying, I'm like, one, this is muscle tissue. If the muscle tissue is dead, is it going to be pumping blood anymore? Nope, it's dead. And I'm like, which yes, and I'm like, you in itself, and if your heart's not pumping blood, that in itself can kill you, because you are no longer pumping oxygenated body. Now, problem with damaging cardiac muscle tissue, I'm like, there's 3 different types of muscle tissue: smooth, cardiac, and skeletal. Which is the only one that can heal itself? Smooth is the only one that can heal itself, which means if you kill cardiac muscle tissue, it's replaced with connective tissue or scar tissue. This new tissue does not contract. It can't sit there and squeeze on those ventricles or atria and make them pump blood. Like when you have a heart attack, even though people will survive, the living tissue, if you didn't kill it all, and I'm like, which Jenna, if you kill it all, you're not living. And I'm like, but I'm like, their living tissue has to try to compensate for all this extra dead tissue. But their heart will always have some type of permanent effect. It will always have some type of permanent damage. So one heart attack has permanent damage on your heart. You cannot heal completely. Okay, if you didn't damage a lot of tissue, you may have other muscle tissue that tries to compensate. It grows wider, larger, just like if you're trying to lift weights. It can try to do the same, but it will never heal completely. Now, some things that we looked at, I'm like, looking at cardiac muscle tissue, yes, it's striated, it has stripes. It's short, it's branched. They're thicker than some of your muscle fibers. They're all connected and interconnected with all those branching to each other. They usually have 1, occasionally 2 nuclei. They have lots and lots of capillaries, bringing lots and lots of oxygenated blood. They also have T-tubules, because they still have to do action potentials. They also have T-tubules. There's not as many. It's not as arranged the same as your skeletal muscle tissue. Your sarcoplasmic reticulum. Do you remember what that does? In your skeletal muscle, we talked about the sarcoplasmic reticulum. It helps with muscle contraction because it stores and releases calcium. And I'm like, however, the sarcoplasmic reticulum, it doesn't have like triads and all this stuff, but it still does the same thing. It stores and releases calcium, which calcium is a big player in muscle contraction. So we still need the sarcoplasmic reticulum. We still need the calcium that's there. It also has lots and lots of mitochondria. About 1/4 to 1/3 of an actual muscle cell is made up of mitochondria. What do mitochondria make? ATP, your cardiac muscle. And I'm like, needs lots of ATP to contract. And because of that, it also needs lots of what to make ATP? We have to breathe it in. Oxygen. It needs lots and lots of oxygen. So your cardiac muscle tissue needs lots of oxygen to make lots of ATP, and it has lots of mitochondria that can do that. Joining or connecting all of these branching tissues, you got to know in lab, are those intercalated discs. These are junctions between the different muscle cells. Now, there's kind of 2 structures. One, connecting the 2 cells, you have these structures called desmosomes. These are the things that are like holding the cells together. We don't want them to pull apart. We want those cells to stick to each other. So desmosomes hold them together. We find desmosomes in our skin as well, holding skin cells together, which is why when you get a sunburn, it peels. It's desmosomes. And I'm like, however, even though they are stuck tightly together, we still want information to get from one to another. We still want them to, talk. And so we have gap junctions, which their name tells you what they are. They're at the junction where two cells are stuck together, and there's a little gap in there. So it allows ions to move from one cell to the other. Because again, moving of ions is very important when you're creating action potentials and wanting muscles to contract. So you have these little gap junctions so they can talk. And so your entire heart, because of all of these gaps, allowing all the ions to flow everywhere they need to, it behaves as a single coordinated unit. Both atria will fully contract. Both ventricles will fully contract. Because they are talking, all the ions are able to flow from one cell to the other. All right, some review. If you got your colored note cards out. What is the double-walled sac covering the heart termed? It is the pericardium around the heart. Of the following layers of the heart wall, which consumes the most energy? Makes you think. Thinking what the different layers are made up of. It's the orange, the myocardium, because the myo is what? This is the muscle. So the muscle needs lots of energy to contract. Which of the following structures is an exception of the general principles surrounding blood vessel oxygenation levels? Generally, when we're talking the rule or the general principle, usually arteries carry oxygenated blood and usually veins carry unoxygenated blood. The exception being the pulmonary. The pulmonary artery has little oxygen. The pulmonary veins have lots of oxygen. The presence of intercalated discs between adjacent cardiac muscle cells causes the heart to behave as oops, there we go. A single unit. And I'm like, I'll tell you the answer. I was going to say, I'm like, oh, I got to have to move this because we haven't talked about this yet. I'll just tell you the answer. And I'm like, it's pink because we haven't talked about the difference between cardiac and skeletal all that much yet. And I'm like, that's another slide coming up. And I'm like, that yes, they're not each controlled by a nerve ending. All right, part B, a little bit more about the actual contraction, what's happening with your action potentials. Now, that's why I need to move that side. And like, there are some differences from cardiac muscle to skeletal muscle. One of them being about 1%. A lot of people don't think that's a lot, but it's enough. About 1% of your cardiac muscles have automatocy. I'm like, or autorhythmicity. It's a horrible muscle. Autorhythmicity. And I'm like, which means they can generate a rhythm. They can contract on their own, generating a rhythm. Your skeletal muscles could not do that whatsoever. Some, doesn't need a lot, but some do. And not all of your cardiac muscle needs nervous system stimulation. Because some of these cells, because some of this tissue can generate its own rhythm, it can decide like, I don't need your brain, telling it to beat. And I'm like, it can say, I need to beat. And it will generate a rhythm. It can also depolarize the entire heart. So like every muscle fiber will depolarize. In our skeletal muscle fibers, and I'm like, we usually do just a couple here and there so our muscles don't tire out. Our cardiac muscle tissue, we make every single muscle all work together to make sure we're pumping all of the blood. And so all of your cardiac muscle cells, that's what cardiomyocytes, contract as a unit, or none do. They all work together. They all pump, or they don't. And I'm like, it depends if information told it to or not. They also have a really long absolute refractory period. And I'm like, and again, this is, after we have an action potential. And I'm like, you can't have another action potential because everything's resetting itself. It has long absolute refractory periods. And I'm like, it's not on there, but there's, 2 reasons. One, it prevents tetanic contractions, meaning your muscle stays contracted and it doesn't relax. That's not good if your muscle stays contracted and doesn't relax, because then blood's not flowing anywhere if it's not constantly beating. Also, having this long refractory period allows enough time for blood to be able to pump from an atria to a ventricle, like all of the blood getting from point A to point B, or from all that blood going from the ventricle and out, wherever direction it's going. Now, there are some similarities between skeletal muscle and cardiac muscle. Now, read through this on your own, because this should look familiar. Look familiar? It's all the basic steps that cause skeletal muscle to contract can help with cardiac muscle contracting. You're still going to open a few channels. And I'm like, they go in, I'm like, when a few sodium ions go in, yes, you're going to have that changing of your membrane potential. And then they can close. You're still going to have depolarization, causing that sarcoplasmic reticulum to release calcium. It binds to troponin. Those actin and the actin and myosin can slide past each other. Same basic ideas, but it's not all the same. Here's the differences. There are still some differences between contraction of the heart versus contraction of skeletal muscle. One, calcium ions play a bigger role. And I'm like, skeletal muscle, calcium bind to troponin, it, really opened up that active site, and that's really the only place you saw calcium. One of the, major, mostly. And I'm like, however, when we have our cardiac muscles starting to contract, the depolarization wave, instead of just opening some sodium channels, it opens some calcium channels, and calcium starts to leak in as well as sodium, which allows that, the calcium going in, it prolongs the depolarization phase. Instead of just going, up and down, we're going to prolong the depolarization. It's going to go up, and then it, kind of stays up. Like, it's called a plateau because you've got all that extra positive ions going in and staying in. And so your action potential and the contraction lasts a lot longer. Again, we want that longer time period so that blood can get out of whatever chamber it needs to and go from point A to point B. And because calcium is active in your depolarization, we also have to take into account of it in the repolarization. And so instead of just closing sodium channels and opening potassium, and I'm like, we also have to close those calcium channels as well, and we're going to have to pump them all back into that sarcoplasmic reticulum for storage for later. So we have to add another extra ion in here. This is showing that plateau. We depolarized, and then it kind of hangs out at that, high charge, allowing longer contraction blood to flow from point A to point B. And you have that long absolute refractory period. Oops. What's going on? Now, we already said this before, cardiac muscle has lots and lots of mitochondria, which means it needs lots and lots of oxygen. It has very little anaerobic ability. Our skeletal muscles, yes, they need lots of oxygen as well, but if you're working out really hard, they can also switch over to anaerobic. Yes, you're sore the next day, but they can switch over to anaerobic. Our cardiac muscles can't switch, or very little bit. They need oxygen. They need all of that oxygen to make all of their ATP. They can't just switch over. Now, other than needing oxygen, they need energy. Now, they don't really care where they get the energy. They can get it from glucose, They can also get it from lactic acid, the thing that makes your skeletal muscles sore. It's still energy. There's still lots of bonds in it. They can use it. They will, they will get their fuel from like anywhere they possibly can, as long as there's oxygen and they can make ATP. Now, the electrical events, this again is showing your depolarization and repolarization. The rhythm can be altered by your autonomic nervous system. What do you remember about your autonomic nervous system? You have no control over it whatsoever. Autonomic sounds like automatic. And I'm like, so your autonomic nervous system, it can change your rhythm. It can make your heart beat a little faster if you need it. And I'm like, or it can slow her down when you're resting. And I'm like, it has, a basic rhythm about how many times your heart beats. Now, your heart beats all coordinated, mostly because you have those gap junctions. Ions can get everywhere. And I'm like, and you have this intrinsic cardiac conduction system, making it so that action potentials go from point A to point B to point C to point D, and nowhere splitting off anywhere else they shouldn't be. So you have some non-contractile cells, non-autorhythmic, and I'm like, they're there to contract, but they don't send electricity. And I'm like, and I'm like, you've got some other cells that can help coordinate depolarization, creating action potentials and sending it from point A to point B. Now, some action potential initiation. One, we have unstable resting membrane potentials. It's because we have this thing called a pacemaker potential. We always have slow, open sodium channels. If you have open sodium channels, sodium's going to sneak through. And I'm like, it's usually never closed completely. And so sodium's always sneaking in. It's like there's always a window open with our club axon. There's always a window open that some sodium can sneak in. You can try to kick all the sodium out. There's always a window. They're always trying to sneak in. And so I'm like, when they're always trying to sneak in, it's like we're almost always ready for an action potential. It's like it's priming itself all the time to hit threshold and do a full action potential. And so the fact that you have these sodium channels always open, the windows open, and sodium always trying to sneak in, we have what's called a pacemaker potential, that it's constantly preparing itself. Your ions are always changing. So you have this ion imbalance, which just makes it your heart's like, I don't know what to do. I got ions moving everywhere. They're never it's never everything's closed. Now, depolarization, yes, sodium are still sneaking in. And I'm like, they're still causing, just like a normal skeletal muscle. Sodium are still going to sneak in. And I'm like, however, those calcium also will sneak in. So it's not just sodium going into the club, sneaking in through the windows. And I'm like, now you have calcium also positively charged. And I'm like, that are going to go in. And when you have two positives going in, you have this huge influx, this huge rise of your action potential. Now, to repolarize, the main thing that we'll leave to eventually get it back down to normal is still your potassium. So it's just, that's the same. However, you have two things going in. So both calcium and sodium going in, creating this huge rise, and like potassium leaving, creating that repolarization. But the fact that sodium are always sneaking in through windows is always making it that the heart always is getting ready to contract again. That's that pacemaker potential. It is, and I'm like, it's always getting ready. I underline it, but I'm like, there is no flat line. And I'm like, before when we looked at it, we're like, oh, it's flat, then it does this, and it's flat again. There is no flat line anymore. We don't want our hearts to flatline. And I'm like, they're always slightly, even it might not be that drastic, but there always is an uptick. And I'm like, trying to get ready to create another action potential. Now, the sequence of where we create or start this action potential and where it travels from. Now, these should sound familiar. Yes? From lab? Because you had to, identify them on a heart, even though I don't think they were even asked on your lab exam. Okay, I looked and I'm like, oh, look, he didn't ask any of them. Sinoatrial node. So we're going to start at the top. Sinoatrial node. Very top of the right atrium. It is the start. It is what's considered the pacemaker of the heart. It's what's going to start the action potentials off which means it's going to start the whole contraction of the heart off. Now, it generates electrical impulses about 75 beats or 75 times a minute. And so on average, we have approximately 75 heartbeats or 75 heart contractions a minute. Again, that can vary among individuals, and what you're doing is just an average. And it will spread across the atria, hence the area, the arrows. Both atria will receive action potentials so that both atria will contract at the exact same time. Other than both atria, all of the muscles receiving this information, this electrical information, at the bottom of the right atrium, the AV node will also receive the information. We just find this in the wall between the atria and the ventricle, so your interatrial septum, and it receives the information, and then there's a slight delay as it's there. Major reason why there's a slight delay, it receives the electrical information, but it doesn't send it on quite yet. And I'm like, it wants to make sure that both of those atria received their information, and they both contract at the same time before we start to send information on. Then it will travel down your atrioventricular bundle, and like it's the only thing that's really connecting your atria to the ventricles electrically wise. There's no other way or no other area that your atrias talk to your ventricles except the atrioventricular bundle. And I'm like, it splits down that interatrial septum just into your right or left. And I'm like, depending on what side of the heart, it will eventually send electricity through. And it's going to send it down to the tip of the heart, the apex of the heart at the bottom. And then they're going to go up the sides in your Purkinje fibers, sometimes called subendochondrial. And I'm like, your Purkinje fibers. Now, when the electricity goes up through the Purkinje fibers in the outside ventricle walls, it will cause the ventricles to contract. Now, the ventricles, and I'm like, as the information goes up, that's the direction that the heart contracts. The heart squeezes and starts contracting at the bottom and then works its way up, which that's what it wants to do, because it wants to be able to pump upwards to send blood up into the aorta or blood up into the pulmonary trunk or atria. There's just a big picture. I just want to get through this slide. Read this slide. And I'm like, only because the other stuff looks familiar. One, if anything is wrong with any of this, it can lead to arrhythmias. It just means your heart's not beating in the same rhythm it's supposed to. It doesn't go atria-ventricle. And I'm like, it starts to kind of go all over. That's never good. And so you can have uncoordinated atrial and ventricular contractions. If they are uncoordinated, it means blood might not be getting to where it needs to in the body. You might also have what's called fibrillation. It's irregular contractions. This is a normal contractions. You've got your P waves, your QRS, your T waves, like atria, electrically contracting, ventricles electrically contracting. Great, it's one-way flow. Fibrillation is you just have electricity all over the heart. It's not going from atria contraction. It's not following, the flow of 1, 2, 3, 4, 5. I'm like, it's just sending electricity all over. This, because there's really no rhythm to it, it's not going to pump the blood from atria to ventricles and out and so forth. And I'm like, so this is called fibrillation. All circulation in the body ceases. The heart's just kind of doing this weird beat, 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 and it's not actually pumping blood out. And I'm like, this, if you're not moving any blood whatsoever, you're not bringing oxygen to anything, it can cause brain death. And to get rid of fibrillation, sometimes you can use a defibrillator, which literally means removing fibrillation. Sometimes, yes, that shock can all of a sudden be like, that shock will get that sinoatrial node back on a rhythm. Not always, but a lot of times it will. If that something happened to that sinoatrial node, it doesn't really know what to do, the electricity is not flowing, that extra shock kind of stops it, and then start it all over again. If you have a problem with your AV node that moves electrical information from atria to ventricles, it's just called a heart block. That just means your atria may contract, but your ventricles don't. Again, you're not moving blood through the body. If your AV node has problems, and I'm like, or even your sinoatrial node, that's when they can put those artificial pacemakers in. That's where we're going to stop. And I'm like, 'cause some of the other stuff, this looks like some lab familiar stuff, and I'll record, the rest of it.